Every morning, without exception, the sun rises. You have seen it happen thousands of times. The same star, the same position in the sky, the same reliable warmth. It has been doing this since before the Earth had oceans, before the Earth had an atmosphere, before the Earth existed at all. For 4.5 billion years, the sun has been exactly where it is, orbiting the center of the Milky Way at a distance of approximately 26,000 light-years, sitting quietly in the outer regions of the galactic disk, going about its business with the dependable consistency of an object that has always been there and always will be. Except it has not always been there. Research published on March 12, 2026, in 2 simultaneous papers in the journal Astronomy and Astrophysics has confirmed something that astronomers have suspected for years, but never been able to prove with this level of precision or at this scale. The sun did not form where it currently sits. It was born somewhere else entirely. Somewhere dramatically different. Somewhere that by every measure we currently understand should have made the existence of Earth, and by extension the existence of everything that has ever lived on it, essentially impossible. The sun was born more than 10,000 light-years closer to the center of the Milky Way than it is today. In the dense, violent, radiation-blasted inner regions of our galaxy, in a neighborhood so hostile to the long-term stability required for life that spending billions of years there would almost certainly have prevented Earth from developing into the world we know. And then it left. 4 to 6 billion years ago, in the earliest period of our solar system's existence, the sun made a journey of 10,000 light-years outward through the galaxy and arrived in the quiet outer disk where it has remained ever since. The question that astronomers have been unable to answer until now is how. Because according to everything we understand about the structure of the Milky Way, that journey should not have been possible. To understand why the sun's origin presents such a fundamental puzzle, you need to understand something about the galaxy we live in that most people never think about. The Milky Way is not uniform. It is not a simple rotating disk of stars distributed evenly in every direction. It has structure. And at its center, that structure includes one of the most significant architectural features of the entire galaxy. A massive bar-like concentration of stars, gas, and dust that rotates at the heart of the Milky Way and stretches tens of thousands of light-years across. This central bar does something important for the purposes of stellar migration. It generates what astronomers call the corrotation barrier, a gravitational effect produced by the interaction between the bar's rotation and the orbital motion of stars in the surrounding region that makes it extremely difficult for stars to travel far outward from the galactic center. Stars born in the inner galaxy tend to stay in the inner galaxy. The corrotation barrier is not a wall. It is not an impenetrable physical boundary. But it is a gravitational obstruction that strongly suppresses the kind of large-scale outward migration that would be required to carry a star 10,000 light-years from the dense inner regions to the quiet outer disk. Full computer simulations of stellar migration in the Milky Way had predicted that only about 1% of stars born at the sun's presumed original location could successfully breach the corrotation barrier and reach the outer disk within 4.5 billion years. 1%. The overwhelming majority of stars born where the sun was born stay where they were born. The corrotation barrier keeps them in. Given this, the sun's current location presents what looks like a straightforward impossibility. The sun's chemical composition tells us clearly where it formed. Stars carry in their elemental makeup a record of where they were born, because different regions of the galaxy have different chemical histories, depending on how many previous generations of stars have lived and died there and enriched the local gas with heavy elements. The Sun is rich in iron, silicon, magnesium, and other heavy elements at levels characteristic of the dense inner regions of the Milky Way, where star formation has been intense for a long time. A star with the Sun's age and chemical composition could not have formed at its current location. The outer disk where the Sun now sits simply did not have enough heavy elements available 4.5 billion years ago to produce a star like ours. So the Sun formed in the inner galaxy. The corrotation barrier should have kept it there. And yet here it is, 10,000 light-years further out than its birthplace, sitting in the quiet galactic suburbs where it has spent most of its existence. For years, this was a puzzle with no satisfying resolution. The Sun was clearly an outlier, a 1% case, a statistical anomaly. The March 2026 research has revealed that it is nothing of the kind. The breakthrough came from Gaia. The European Space Agency's Gaia satellite operated from 2014 to 2025 and produced the most comprehensive map of our galaxy ever assembled, tracking the positions, motions, temperatures, surface gravities, and chemical compositions of more than 2 billion stars with a precision that no previous instrument had come close to achieving. Gaia did not just tell astronomers where stars are. It told them what they are made of, how old they are, how fast they are moving, and in which direction. It turned the Milky Way from a rough sketch into a detailed three-dimensional portrait with the individual properties of billions of objects precisely measured and catalogued. A team led by Daisuke Taniguchi at Tokyo Metropolitan University and Takuji Tsujimoto at the National Astronomical Observatory of Japan used Gaia's latest data release to build something that had never existed before. A large precision catalog of solar twins. Not stars that are broadly similar to the Sun. Exact matches. Stars with the same temperature, the same surface gravity, the same chemical composition, and critically the same kind of age that can be determined with high precision from those properties combined. The catalog contained 6,594 solar twins within roughly 1,000 light-years of Earth. This is approximately 30 times larger than any previous solar twin survey ever compiled. When the team examined the age distribution of their 6,594 solar twins, they found something that immediately stood out. The distribution was not smooth. It was not the gradual spread of stellar ages you would expect from a random sample of stars that formed at various times in the local neighborhood. Instead, it showed two distinct concentrations. A younger group of stars, around 2 billion years old, that appeared to have formed locally in a relatively recent burst of star formation in our region of the galaxy. And a much larger older group, 1,551 stars, concentrated between 4 and 6 billion years old. The Sun falls within that older group, and the stars in that older group share something beyond just their age. They share their distance from the galactic center. They are all sitting at approximately the same orbital radius from the Milky Way's core. A large population of stars, all the same age, all at the same galactic radius, all with chemical compositions pointing to an inner galaxy origin. The probability that this clustering is coincidental is essentially zero. The Sun did not make the journey alone. It was part of a mass exodus. Thousands of solar twins all migrating outward from the inner galaxy at roughly the same time in the same direction to the same destination. Not a gradual drift over billions of years, but a concentrated migration event that carried an entire cohort of stars 10,000 light-years outward in a relatively brief period of cosmic time between 4 and 6 billion years ago. The question is what caused it. The answer that Taniguchi and his colleagues propose is elegant in the way that good science often is. It explains not just one puzzle, but two simultaneously. Remember the corrotation barrier. the gravitational obstruction created by the Milky Way's central bar that should have prevented this migration from happening. The new research proposes that the corrotation barrier did not stop the migration because it did not yet fully exist when the migration occurred. The galactic bar itself was still forming. Current estimates place the formation of the Milky Way's central bar at approximately 6 to 7 billion years ago. If this is correct, then the bar was in the process of assembling itself from a chaotic collection of inner-galaxy material into the coherent rotating structure it is today at almost exactly the same time that the solar twin migration was taking place. A bar that is still forming does not yet generate the same corrotation barrier that a fully assembled bar produces. The gravitational landscape of the inner galaxy during the bar's formation period was fundamentally different from the gravitational landscape of the inner galaxy today. More than that, the violent process of the bar's assembly may have actively driven the migration rather than simply failing to prevent it. As the galactic bar condensed and began to rotate, it churned the surrounding stellar orbits through a process called radial migration, generating gravitational perturbations that diffused the angular momentum of nearby stars and sent them sailing outward through the galaxy. The Sun and its thousands of twins did not fight their way through a barrier. They rode the gravitational wave created by the barrier being built. This is the mechanism. 4 to 6 billion years ago, as the Milky Way's central bar was assembling itself into the structure we observe today, its formation triggered a large-scale exodus of the inner galaxy's stellar population. A cohort of thousands of solar twins, including our own Sun, caught that gravitational wave and rode it 10,000 light-years outward to the quiet galactic suburbs they now occupy. The Sun's chemical composition, the ages of its stellar twins, and the dynamics of the galactic bar all tell the same story. The migration happened, the bar formation drove it, and the Sun was part of it. Now comes the part of this story that makes the science personal in a way that goes far beyond astronomical curiosity. The inner galaxy where the Sun was born is a fundamentally different environment from the outer disk where it now sits. The differences are not subtle. They are the difference between habitable and uninhabitable at the scale of planetary systems. The inner regions of the Milky Way are dense. Stars are more closely packed. Stellar interactions, close gravitational encounters between neighboring stars, are more frequent. Supernovae, the explosive deaths of massive stars that blast surrounding space with lethal high-energy radiation, occur more often because there are simply more massive stars being formed and dying in that region. The radiation environment of the inner galaxy is significantly more intense than the outer disk. For a young planetary system trying to build stable orbits around a newborn star and then develop the conditions required for life to emerge and persist over billions of years, the inner galaxy is an extraordinarily hostile neighborhood. The outer disk where the Sun now sits is quieter. Stars are more widely spaced. Supernovae are less frequent. The radiation environment is gentler. The gravitational perturbations that could destabilize planetary orbits are less severe. It is, by the measures that matter for the long-term stability of planetary systems, a significantly more benign location in which to spend 4.5 billion years. The Sun's journey from the inner galaxy to the outer disk may have delivered the best possible outcome for the development of life on Earth in two separate ways simultaneously. The first is the raw materials. The inner galaxy where the Sun was born is chemically rich. Generations of massive stars living and dying in the dense inner regions have seeded the gas there with the heavy elements that planet formation requires. Iron for Earth's core, silicon for its mantle and crust, oxygen for its atmosphere, carbon for the molecular basis of all biology. These elements are relatively scarce in the outer disk, where the Sun now sits. A star forming in the outer disk 4.5 billion years ago would not have had access to the same concentration of planet-building materials. The Earth's composition, and by extension, the chemical foundation of all life on Earth, reflects a birthplace in the enriched inner galaxy rather than the depleted outer disk. The second is the stability. The inner galaxy's hostile radiation environment and frequent stellar interactions would have made the long-term development of complex life on any planet in that region extremely difficult to sustain. The early solar system needed time, billions of years of relative stability during which the planets could settle into their current orbits, the Earth could develop its oceans and atmosphere, and life could emerge and gradually diversify into the complexity we observe today. That kind of stability is far easier to maintain in the quiet outer disk than in the crowded, violent inner galaxy. The Sun was born in the right place to build a planet like Earth. It migrated to the right place to keep it stable long enough for life to evolve on it. The journey between those two places is not incidental to our existence. It may be one of the reasons we exist at all. Taniguchi himself stated it clearly in the research. The galactic migration likely carried the solar system from a more hazardous inner region to the quieter outer disk early in its life, allowing it to spend most of its lifetime in a comparatively stable environment. This would have allowed the conditions for life to develop and persist on Earth. There is one further layer to this story that extends its significance beyond the specific case of our solar system. The ages of the 1,551 solar twins in the migrated cohort do not just tell us when the Sun left the inner galaxy. They constrain the timing of the galactic bar's formation with greater precision than any previous method has been able to achieve. The bar had to be in the process of forming when the migration occurred to have driven it. The migration occurred between 4 and 6 billion years ago. Therefore, the bar began forming at least 6 billion years ago and completed its formation sometime after the migration was complete. This is a genuinely new constraint on one of the most debated questions in Milky Way archaeology. When did the central bar form, and how quickly did it develop? Previous estimates placed bar formation at various points between 6 and 10 billion years ago with wide uncertainty ranges. The solar twin migration data narrows that window significantly. The bar's formation timeline and the solar system's origin story are written in the same dataset of 6,594 stars. Two questions answered by the same evidence. We knew for years that the Sun had come from somewhere closer to the center. The composition told us that. What we did not know was that it had not made the journey alone. That thousands of identical stars had made the same migration at the same time, driven by the same gravitational event. That the journey was not a rare statistical anomaly, but the product of a specific moment in galactic history, when the forming bar of the Milky Way caught an entire generation of stars and sent them sailing outward together. The Sun we orbit every day. The star that makes all life on Earth possible. The object so familiar and so constant that its daily rising feels like the most dependable thing in the universe. It came from somewhere else. It made a journey of 10,000 light years. And we exist because it did.